And my apologies to the group theorists here who already know the Kroll-Schmidt theorem very well for groups. For me, I always assumed that there was a Kroll-Schmidt theorem for finite groups that just said that everything factors uniquely up to isomorphism, that every group factor, you got two factorizations of a finite group as a product of indecomposables, then they're isomorphic piece by piece, and it was only when a referee pointed it out to me that I discovered that it's really a much stronger theorem and a much more useful theorem. So I'm planning to spend, most of the talk on the theorem for groups, and then at the end explain how to convert that to proof in the theorem for fusion systems. The group theorists who already know the theorem can maybe use the time to speculate over how one does this for fusion systems while I'm talking about the group case. Okay. I'm talking almost entirely about finite groups, but I thought I'd at least state the theorem in its almost full generality at the beginning. And so that's why I'm including the definition of a Cheat series of G as a finite sequence of subgroups, all normal in G, such that each is maximal in the following one with that property, maximal among, so that Hn minus 1 is, or Hi is maximal in Hi plus 1 among normal subgroups of G properly contained. And so this, of course, is going to be the condition in general for there to be a Kroll-Schmidt theorem for G. And then G is indecomposable. Well, I think everybody knows what that means, but I thought I should put it in just for form's sake. And then the key definition, concept, used in the proof is concept of a normal endomorphism of a group, meaning an endomorphism that commutes with all inner automorphisms. And my interpretation of the proof is that the proof of the theorem is that it's this definition that makes it possible essentially to prove this result for groups, making essentially the same manipulations as one does for, say, vector spaces or modules when proving uniqueness of a direct product or direct sum decomposition. So one of the key examples is an idempotent endomorphism of G. Projection to a direct factor is always normal. And G is abelian, then of course all endomorphisms are normal. Maybe I should add the observation that the image of a normal endomorphism is normal in G, which could be the original motivation for the name. And then just as notation, I'm using a superscript n to denote normal. So end upper n, odd upper n for normal endomorphisms or isomorphisms of the group G. Let me also add that the approach I'm taking was taken directly from Suzuki's book, volume 1 of his, I think it's called Group Theory, his 2-volume work anyhow. And basically what I did, I mean, when I was writing a paper on the theorem for fusion systems, I used that as a guide, his proof as a guide. And then when I wanted to prepare this talk, I used the paper on fusion systems for a guide to translate back to groups. So that's just to say how close the two proofs are, that for finite groups and for fusion systems, it's almost the same. Okay, so the Kroll-Schmidt theorem says, assume the group admits a chief series, which of course includes all finite groups. Then G is a finite product of indecomposable groups, and in a way that's unique up to normal automorphism of G. So if you've got two factorizations like that, then you've got the same number of factors, and there's a normal automorphism of G that sends each factor in the one decomposition to a factor in the other decomposition. And this is the way in, well, I'll talk later about some consequences of why it was important for us to know this. But, well, I can just say now that it has, my interest came up because of consequences for automorphisms of certain groups. So, as I said, it's a very general formulation, not just restricting to finite groups, but it's not the most general formulation. I didn't want to put that down because I find it more confusing than clarifying to put it down. But more generally, and the way it's formulated in Suzuki's book, and also in Huppert, I think I remember, yeah, so you take a group of automorphisms and then insist that all subgroups, normal automorphisms and everything else commute or be invariant under that group of automorphisms, and then gives you a separate definition of indecomposability and so forth. But again, I'm not going to say anything more about that. Okay, yeah, so as I say, for now on, focusing on finite groups. And just basically start off looking at basic properties of normal endomorphisms, where starting point is just to do the opposite obvious. You look at the, let's see, just look at the definition, that's this first equality, and then apply the fact that 8 is a homomorphism, and you get that x inverse eta of x has to commute with eta of y for all x and y. And so that gives you two subgroups that have to commute with each other in G. And so one consequence of this is particular that the kernel and the image of any normal endomorphism have to commute with each other. Okay, and another consequence for automorphism, normal automorphisms, and this is where my interest first came up. For normal automorphisms, it says that a normal automorphism has to be the identity on the commutator subgroup, and on G mod the center. And so G is center free or perfect, then the only normal automorphism is the identity. And when I go back to the theorem that says that in this case, when G is center free or perfect, the direct factor decomposition is unique. Not just unique up to some form of isomorphism, but unique on the nose. Okay. And so this is a easy consequence of that key lemma there, that the image commutes with certain elements. Okay, and so I'm just repeating here what I said before about what the Kroll-Schmidt theorem, Kroll-Remak-Schmidt theorem says in the case of when G is center free or perfect. Okay, and this is the consequence that was important, well, for especially in some of my work with Carlos Albert and Jesper Müller, that when G is perfect or center free, then its automorphism group can be described explicitly in terms of automorphism groups of the indecomposable factors. And of course, I didn't bother to write it down, but of course one can say exactly what gamma is. It's the permutations of K elements which only permute indices of factors that are isomorphic. So in other words, the requirement is that if sigma is in gamma, if and only if H sub I is isomorphic to H sub sigma I for all I. So now, and one of the key properties of normal endomorphisms is that they always split. And again, it's very elementary proof. So it splits, G splits as a product of two subgroups, direct product of two subgroups, where the endomorphism is restricts to an automorphism of one and a nilpotent endomorphism of the other. And well, in the case of finite groups, it's straightforward because you just take n large enough so that the images of the nth power, eta to the n, and the kernels of the eta to the n stabilize. And then H is the image, this stable image. K is the stable kernel. You can also state that as the intersection of all the images of eta to the I, the union of the images of the kernels. And then it's clear that eta of H equals H. It's clear that I see that, yeah, that F should be an eta. I changed notation after writing the slides and then overlooked that one thing. So it's clear that eta to the n is 0 on K, and so on the factor K, and so eta is nilpotent on K. And then the rest is straightforward. And in fact, the only place that normality is used is in order to say that K is normal and commutes with H. Otherwise, if it were an arbitrary endomorphism, you'd get a semi-direct product with K normal and H, K semi-direct product with H, with those same properties. But of course, since we're talking about indecomposables, then it's crucial to know that you do get a semi-direct product. Okay, so here's where I just wanted to list some of, the key properties. Is this visible over here? Yeah. So for eta, so the first one was that kernel and the image commute. Second, that if eta is an automorphism, then it's the identity and it's also the identity on G mod at center. And now the third one, that if G is indecomposable, then eta has to be an automorphism or nilpotent. Okay. And of course, the corollary follows immediately. Now, the idea is going to be to manipulate the idempotence corresponding to the direct factors in the same way that one might do it for when working with direct sums or products of modules. So, need to talk about summability and sums of homomorphisms. And that just means that you take, you take their, you multiply their images. So you say that a set of homomorphisms from G to H is summable if their images commute pairwise. And if that's the case, then you define their sum, eta 1, sum up to eta k, by, well, element-wise, by taking the product. And, well, I know the terminology, mixing multiplication and addition, confused me at first, but sort of unavoidable. For one thing, it's clear from the definitions that the sum, well, for summable endomorphisms, the sum is commutative because the images commute pairwise. But also, it's necessary just to keep it distinct from composition as an operation on endomorphisms. And for consistency, I'm calling it 0, the neutral element for sums of endomorphisms or homomorphisms. And and then the obvious example and the important example for what we're looking at is if you take the projections to the factors of G. If you've got a direct product decomposition, take the projections to its factors, then they're all normal. We already noted that. They're summable, and their sum is the identity on G. Okay. And I guess, I mean, I was just following the, copying the notation used in Suzuki's book, but I guess the main reason for calling it a sum, aside from distinguishing it from composition, is because composition is distributive over these sums whenever defined. And so something one has to check, but is extremely elementary to check, that that you've got a product of two or a composite of two sums, then that's the sum of all of the possible composites. And that includes the statement that these four or however many terms are summable, meaning that their images all commute pairwise. Okay. And then, yeah, sum or composite of normal endomorphisms is clearly normal. And I'll be coming back to that point when I start talking about fusion systems. But, and then giving one more special case, which comes up in the proof, namely that if you've got two endomorphisms whose composite in either direction is 0, is the trivial endomorphism, then, yeah, two normal endomorphisms whose composite is 0, then they're summable. And so their sum is clearly normal. And again, that's almost immediate from the earlier relations. And now, for the key property that makes this all work, when proving the Crowell-Remak-Schmidt theorem, is that if G is indecomposable, well, we already saw that if G is indecomposable, then every normal endomorphism has to be an automorphism or nilpotent. And now, if you've got G is indecomposable, and if you have a summable set of normal endomorphisms whose sum is an automorphism, then at least one of the summands, one of the eta I has to be an automorphism. And I think it's worth pointing out here, I mean, what the key point is, because if well, what you know is that if none of them are automorphisms, if none of the A to I are automorphisms, then they all have to be nilpotent. And so it's tempting to think that, okay, got a sum of nilpotent things, then the sum has to be nilpotent, except that that assumes that they commute pairwise, commute under composition, which need not be the case. You could have A to 1, A to 2 different from A to 2, A to 1, and then that type of argument doesn't work. So instead what one does is start off with some reductions. First, observe that it's enough to do it when k equal 2, and then do the general case by iteration. And secondly, when k equal 2, then it's enough to do it when the sum is the identity. Again, just by composing with the inverse of the sum. And once A to 1 plus A to, once you've got A to 1 plus A to 2 equal the identity, then it's easy to check that A to 1 and A to 2 commute with each other. And so, and afterwards use the usual argument. Yeah. Wait. I didn't click the wrong button. Okay, yeah. Use the usual argument to show that the sum has to be nilpotent and can't be an automorphism. Can't be the identity in particular. Okay. So now I decided to, well, put the entire proof of the theorem on two pages here, 2 slides. So just this indication of how simple it really is. And of course, there are lots of details, but anyhow, start off with two different decompositions, direct factor decompositions, direct product decompositions. All of the factors are indecomposable and non-trivial. And then just separate out H1 star and let K be the product of all the other factors in the second decomposition, H2 star to HM star. And then look at the idempotence. So A to 1 to A to K for the H1 to HK, and then let theta be the idempotent for H1 star and theta prime for the other factors. Okay, and by remarks earlier or by, well, it's clear that we have these relations. And now take the composite and composing from right to left of some of the A to I's followed by theta, so that's theta, and then restrict it to H1 star. And remember that H1 star is the image of theta, so that all of these restrictions are endomorphisms of H1 star. We have just a sum of some endomorphisms of H1 star. Know that the sum is the identity because theta was the idempotent for H1 star. And so by the result just shown, and since H1 star is indecomposable, one of those factors has to be, one of those summands has to be an automorphism of H1 star. And so we get this situation The image, well, so we were looking at the composite A to J followed by theta. And so take A to J, that has the image in H sub J, and then followed by theta restricted to H sub J. And we just saw that that's an isomorphism, and that the composite's an isomorphism. And one has to, I mean, the claim, of course, is, the key point is that both of those have to be isomorphisms. And, well, so that means showing that the other composite is an isomorphism. And I wrote down a proof on there, but that's basically, it's just the fact that we know that all endomorphisms, all normal endomorphisms of H sub J have to be automorphisms or nilpotent. And if you've got a pair of homomorphisms between two groups where one composite is an isomorphism, then the other composite cannot be nilpotent. I mean, there must be lots of different ways of checking that. So both of these are isomorphisms. And of course, we're already, now after this, it's just a matter of getting the right manipulations, because we've already shown now that, or we have shown now that H1 star is isomorphic to one of the factors in the other decomposition. And then, so now, we've got, so theta followed by A to J is an isomorphism, automorphism of H sub J. And then noting, as we saw earlier, if you have a composite of two endomorphisms, if the composite is 0, then the endomorphisms have to be summable. And since theta and theta prime were idempotents for distinct direct factors, the composite is 0. Okay, so those are summable, and now the rest of the proof, you just take their sum and then check that it, that first, in fact, the only hard part is checking, it's not really hard, checking that it's an automorphism of G, and it's clearly the identity on, well, it sends H1 star isomorphically to HJ, and it's the identity on the other factors, H2 star and so forth. So, and okay, so we get a normal automorphism of G with this property, sends H1 star to HJ, all of the others to themselves, and then you just keep repeating that with the other factors, HI star, and take the composite of those normal automorphisms. Okay. So now the question is, how does this work for fusion systems? And when I wrote these slides, I'd forgotten how many people were going to be talking about fusion systems here before I was. So I don't think the background is really needed, except maybe as a quick refresher for some of the people who hadn't seen fusion systems before. Let me add that what I'm talking about here directly is the corresponding, what I'm going to state shortly, is the Kroll-Remak-Schmidt theorem for fusion systems over finite p groups. But in fact, it turns out to be almost as simple to prove the theorem for fusion systems over discrete p-Toral groups. And so it was that version that I wrote up in the paper, just in case it's useful someday. Okay. So the key, the key question is going to be, well, first you have to get the right conditions for, well, first you have to define endomorphisms of a fusion system, although there are already standard definitions. Then you have to define what conditions you want for summability, and then the most important step was to define what you want for a normal endomorphism. Okay, so so I'm giving, well, the definition I'm giving of morphism of fusion systems is certainly the one one finds. It's not the only possible definition, but it's the one finds most often. And most importantly, it's the one that is needed in this situation. So I'm first defining it motivationally. A morphism from E to F is a pair, a homomorphism, and a functor, a homomorphism from T to S between the underlying P groups, and a functor between the categories that agree in the obvious way, namely, the functor sends P to eta of P, to its image under eta, and on objects and on morphisms, you require that this diagram commute, these squares commute for all morphisms in E. Yeah, as I said, this isn't the only one, because I think Andy at one point, Andy Chermak, was working with a definition where he didn't require where eta hat could send an object P to anything containing eta of P, not necessarily its image under eta. But one of the advantages of this restriction, this definition, is that the homomorphism eta does determine the functor eta hat. And so normally, most of the time, one just defines a morphism between fusion systems to be a homomorphism for which there is an associated functor between the categories. And now the product. One more remark I wanted to make. The image, this was something that took me a long time to realize, that it's not at all obvious. If you define the image of a of a morphism to be the image, I mean the category, which is, or no, just the image of the functor, then it's not at all obvious that it's a saturated fusion system. And in fact, not at all obvious that it's a fusion system at all. So not at all obvious that it's a category. So those are true. All three of them are true, but it requires a fairly complicated proof, which I think Pooch proved it in his book, and so that must be the first published proof of it. And then it's also in my book with Aschbacher and Radha-Kesar, where Michael wrote down a complete proof. The one I like best is, and I think is most readable, even though is the one in David Craven's book on fusion systems, although I have to confess that I don't think I've read any of them in full detail. Okay, so, but anyhow, it is a theorem that, at least for fusion systems over finite p groups, the image of a morphism is always saturated fusion subsystem of the target. Okay, now products, that's much more straightforward. I think any of you who've worked with fusion systems have worked with products. And this shouldn't be taken as a complete definition because I'm only talking about morphisms between objects of a certain form. But morphisms between objects that don't split as a direct product are subgroups of S1 cross S2 that don't split are defined by restriction from this sort of thing. Well, yeah. Okay. And now, before defining summability, one has to define commuting fusion subsystems. And this has been done in various ways. Ellen Henke has a different definition of commuting subsystems in one of her papers, which is, of course, completely equivalent. I find it most natural to say that it's that the subsystems commute if you've got a morphism from their product to F that extends the inclusions. I guess Aschbacher in his papers never really says that the fusion subsystems commute. He always interprets it as saying that that their central product exists, but meaning more or less the same thing. But anyhow, this is one way of looking at commuting subsystems. And then one can write down explicitly what this means without reference to morphisms. And so if you've got some morphisms from E to F, then they're summable if their images commute. And so just as in the group case, and in that case, one defines the sum in the obvious way. And one has to check, so their sum is clearly a homomorphism of groups, homomorphism between the P groups, but one still has to check that, that it's straightforward to check that it is a morphism of fusion systems. Okay. And now, when defining normality, the problem is what makes everything easier in the group case is that one just defines a normal endomorphism to be one that commutes with the inner automorphisms. For fusion systems, there aren't enough inner automorphisms, really. I think that's the way to say it, because the closest thing, if we're looking at thinking of a group G and the fusion system F, then closest thing to inner of G is to inner automorphisms of G are, well, ought sub F of S. But that's simply not enough. In other words, saying that an endomorphism commutes with all elements of ought sub F of S, simply not strong enough to do what we want it to do. But instead, there's a very nice, simple criterion, which just says that there's some other endomorphism, chi, such theta and chi are summable, and their sum is the identity on F, or meaning the identity on S, on the P group. And sorry to keep you jumping. Maybe I'll just leave it as an exercise for people not already familiar with it, that if you've got eta, an automorphism of G, or an endomorphism of G, is normal if and only if the same condition happens. There exists chi, an endomorphism such that eta plus chi is the identity on G. And yeah, in one direction that follows from almost immediately from some of the things written earlier and long since disappeared. But okay. But let's. Okay, I know. I just want to make one quick comment that one problem with this definition is that, well, for groups, endomorphisms of groups, it's obvious that a sum of normal endomorphisms is normal, because if each of them commutes with all inner automorphisms, and so does the sum. Here, it's not at all obvious in the case of fusion systems, and I simply don't know. I didn't care enough to spend a lot of time trying to show it. But I guess I proved it in the only case that mattered. But so in general, I don't know whether a sum of normal endomorphisms of a fusion system is, again, normal. Okay, and now can state the Kohl-Remak-Schmidt theorem for fusion systems. I probably should have written fusion systems over finite P groups. Well, I did in the statement of the theorem. In fact, think, yeah, the theorem still holds as stated, precisely as stated, if I replace finite p groups by discrete p-toral groups. That if you have, so in each case, it's obvious that there exist direct product decompositions, finite direct product decompositions, product of indecomposables. And if you've got two of them, then there's a normal automorphism that sends one to the other. Here, oh yeah, that should be in, yeah, let me keep forgetting that people can't see there. So yeah, that, the second case should be an M. Thanks, Paul. Okay, and then you have the same number of factors and so forth. Okay, so particular, not stated it, but well, by essentially the same argument as for groups, if center of F is trivial or over P of F equals F, meaning the focal subgroup of F is the entire thing. I won't define, this is aimed at the experts. Then the identity is the only normal automorphism, and so this factorization of F is unique. And as noted here, the main, almost the only tricky point in translating from the proof I found in Suzuki for finite groups to this case, at least for fusion systems over finite p groups. The only tricky part was choosing the definition of normal endomorphism. It's a little harder, little trickier when working over discrete p-toral groups, because in many cases, one has to replace nilpotent by locally nilpotent, meaning that every element gets to 0 under some power of the endomorphism. And then I'm finishing with just the same consequences mentioned for the groups. And this is what came up, or a special case of this is what came up in my paper with Jesper Müller, Carlos Broto, and Albert Ruiz, that if you've got if you're looking at the automorphism of this product, if F is either center-free or, well, the fusion system equivalent of being perfect, then you can describe odd F in terms of the automorphism groups of its factors as a semi-direct product in this same form. Okay, and that's all, yeah.
Thank you very much. Are there questions?
I'll ask a question. I just wonder about the relationship between normal endomorphism of a group and normal endomorphism of a fusion system. Is it the case that you can produce a normal endomorphism for a fusion system from a group? And also, can you deduce the Kroll-Schmidt theorem for fusion systems from the Kroll-Riemack-Schmidt theorem for groups?
I'm not sure I understand your first question. In fact, I don't understand the first question. As noted here, the condition that I gave for, the definition I gave for normal endomorphism of a fusion system is, I mean, that criterion I mean, that translates directly into an equivalent definition of normal endomorphism of a group. That it's, an endomorphism of G is normal if and only if it's the sum with some other endomorphism is the identity. But other than that, I'm not sure. Maybe repeat the question.
I just wondered, so maybe perhaps if the automorphism, say, preserves the underlying P group of the group or something, can one produce a normal endomorphism for the fusion system using it or something like this?
In general, no, because, well, depends on how you mean using that. But for example, if you've got a normal automorphism of the group, of the P group, then that just means that it's the identity modulo the center P group and the identity on the commutator subgroup of the P group. But the center of the fusion system could be a lot smaller, and the commutator of the fusion system could be a lot bigger. So.
Okay.
But doesn't JSON mean like an automorphism of the group? Like if the fusion system comes from a group, then the question, as I understood it, was what's the relationship between these normal automorphisms of the group and the normal automorphisms of the fusion system?
Yeah.
And I guess a normal automorphism of the group should give a normal automorphism of the fusion system, but
the other way around
the other way around not so clear, right? Yeah.
Yeah, because that endomorphism that you add to make the identity does not have to necessarily come from an endomorphism of the group. I mean, not obviously. Right? I mean, so.
Right.
Right?
Yeah,
right.
That question. Yeah. That sounds right.
Is it totally clear why these are consequences? Is in particular that if the center is trivial or the focal subgroup is the whole thing, then there are no of these normal endomorphisms. Is that clear?
Well, it's basically the same proof as for groups. I'd have to go back just a minute. Well, no, I guess because for groups you used heavily the fact that you use directly the fact that it commutes with inner automorphisms to get started. But well, if you want to wait 5 minutes, I can look it up in my paper. But well, exactly what went into it, but it's not deep. It's not at all. There's nothing deep there. It's well. Oh wait, just a minute. Okay. Okay, so you've got the definition of a normal endomorphism. So now restrict to the specific case where eta is an automorphism. That means that, well, if you look at the definition of summability, that means that chi, the other factor, has to go into the center. It's the center of F, not just the center of F.
Okay, yeah. So it's the same proof as for groups. Okay, yeah. Okay.
That's, yes, right.
Okay, yeah, okay, thanks.
That's the idea.
Right. So all of your manipulations here, you're able to keep it on a fusion system level, right? Some of these things are, sometimes it can be useful to pass to a linking system because there you have an automorphism of the whole linking system, and you don't have to sort of worry about, all these different structures. But you don't do that at any point, right?
Linking systems don't come into it all to the.
Yeah, right.
But actually, my question was related to that Does one get a statement about linking systems from this? I mean, it should say something about linking systems.
Well, it should. Well, okay, obviously, depends on what you mean, because obviously you've got a direct product decomposition of the fusion system. You got a direct product decomposition of the linking systems.
Yeah.
I'm not sure what more information you could get. Or what more it could say about the linking systems. I didn't think about that, in part because it was so nice to be able to, for once, write a paper where linking systems didn't come in. And but, you know, keep it short.
But I mean, there's a subtle difference, right? Because automorphisms of linking systems are different at the prime 2 than from fusion systems, right? So it's not. I mean, so the objects are the same, but the morphisms are a little bit different. So. I mean, I'm sure it doesn't matter, but there's a little bit to figure out.
Except that you've got the map, the homomorphism from odd of L to odd of F. And so any, well, if one can define a normal automorphism of L, then it'll induce an automorphism of F, which presumably is normal. And I'm not, so maybe, I guess I'm not completely sure where you're going, because of course you're not going to restrict to certain normal automorphisms by doing this, because you know that if you have any normal automorphism of F, you can get a second direct product decomposition just by letting it act on the first one. And also, well, maybe more to the point, the center of L and the center of F, I think, are the same. So these conditions that, I guess I didn't write it explicitly, but every normal automorphism of F is the identity modulo the center and the identity on the focal subgroup. And but at least if the center is contained in the focal subgroups, that means that every, well, in general, that's an only if statement. An automorphism is normal if and only if it satisfies those two conditions. And so that.
And there are conditions on the fusion system, you say. So. Well,
only to the extent that the center and the focal subgroup depend on the fusion system, yeah. But they're.
But they do, right? So.
Yeah.
We proved that.
Any other questions? If that's not the case, we thank Bob again.